Okay, so how is the hyperpolarization that we just talked about of the photoreceptors transmitted through the retina and onto the brain? So the photoreceptors do not generate action potentials, and neither do the bipolar cells that come next. They only generate graded potentials, again, similar to the ones that we saw in the neuron. So photoreceptors generate receptor potentials, and the bipolar cells generate either excitatory or inhibitory postsynaptic potentials. So if we're talking about something that's excitatory potential, it's going to cause depolarization. If we're talking about something that's causing an inhibitory potential, then it's going to cause hyperpolarization. So let's just take a look at a couple things right here as illustrated in this image. So if we're talking about in the dark, what happens? Well, our cyclic GMP gated channels are open and we're going to have cation influx. Our cations are sodium and calcium that are going to come into the cell. So if we have positively charged ions coming into the cell, that's going to cause the photoreceptor cell to depolarize. Then we're going to send the signal to the next step, and our voltage gated calcium channels are going to open because we've had depolarization. The neurotransmitter is released continuously, and it's going to cause inhibitory postsynaptic potentials in the bipolar cell, or IPSPs. This is going to result in hyperpolarization because we are talking about an inhibitory signal. Once we have hyperpolarization, this is going to cause our voltage-gated calcium channels to close in our bipolar cell. And this is not going to allow for neurotransmitter to be released from the cell. So we have no excitatory postsynaptic potentials occurring in the ganglion cell, and no action potentials occur along the optic nerve. The opposite is going to be true if we're in the light. So we have our cyclic GMP gated channels are going to be closed, so we don't have any sodium or calcium entering into the cell. So because we don't have any positively charged ions entering, the photoreceptor cell is going to become more negative, so it's going to hyperpolarize. Our voltage gated calcium channels close in the synaptic terminals of the photoreceptor cell, and we have no neurotransmitter being released. In our bipolar cell, because we don't have the inhibitory postsynaptic potentials occurring, we're going to end up with depolarization. And the depolarization in the bipolar cell is going to cause voltage-gated calcium channels to open, which are going to allow calcium to come in, which is going to cause neurotransmitter to be released. So then we are going to send excitatory postsynaptic potentials to the ganglion cell, and we're going to end up getting an action potential that's going to propagate along the optic nerve. So rhodopsin is very, very, very sensitive. In bright light, we typically have bleaching occur so fast that the rods are virtually non-functional, but the cones can still respond. So activation of the rods and cones is going to be depend on both light adaptation and dark adaptation. So light adaptation occurs when we are moving from a dark area into a bright light. For example, if we're leaving a movie and then walking outside in broad daylight. For temporarily, just for a split second, probably all we see is white light because the sensitivity of our retina is still kind of set for that dark light or that dim light. So both rods and cones are strongly stimulated, and we have large amounts of visual pigments break down almost instantaneously, and this is going to produce a huge flood of signals that kind of accounts for the glare that we experience when we go from a very dark area to a very bright area. So we do have some accommodations that are going to occur when we encounter this situation. So the rod system is actually going to turn off. So all the transducins are going to migrate to the inner segment, uncoupling the rhodopsin from the rest of the transduction cascade. If we don't have transducin in the outer segment, then light hitting rhodopsin can't produce a signal. At the same time, the less sensitive cone system and the other retinal neurons are rapidly going to adapt, and our retinal sensitivity is going to decrease dramatically. So within about 60 seconds, the cones that are initially overexcited by the bright light are sufficiently desensitized to kind of take over. The visual acuity and the color vision are going to continue to improve over the next 5 to 10 minutes. So during light adaptation, we really lose retinal sensitivity, which is our rod function, but we do gain visual acuity. Dark adaptation is pretty much the reverse of light adaptation. So it occurs when we go from a really well lit or bright area and enter into a dark one. So initially all we see is just blackness, and that is because our cones stop functioning in the low intensity light. And the bright light bleached our rod pigments, and the rods are still turned off. But once we're in the dark area, our rhodopsin is going to begin to accumulate, and our transducin returns to the outer segment, and our retinal sensitivity increases. So dark adaptation takes a lot longer than light adaptation, and it could take several hours for us to kind of adapt to the dark. There is usually enough rhodopsin within 20 to 30